Welcome to Tomorrow Unveiled.
And thank you for joining us. We're about to get into a week that honestly feels less like a forecast and more like we're documenting a fundamental shift in the history of artificial intelligence.
That is the perfect way to put it,
Yeah.
because the period from December 29th, 2025 through January 4th, 2026 was not some quiet holiday week.
Not at all.
No. Based on the mountain of material our research team pulled together, this was a genuine seismic inflection point. We're seeing a clear move away from what everyone called the Cambrian explosion of generative models.
Right, the AI that just talks or writes.
Exactly. And we're moving squarely into what the research team is calling the era of physical and architectural execution.
And that phrase, architectural execution, that's really the heart of it, isn't it? The biggest breakthroughs we saw, they weren't just about throwing more servers at the problem or, finding more data to scrape from the internet.
No, that was the old way.
That was the old way. This is about deep, elegant engineering. It's about solutions that are pushing up against the very physical limits of what computers can do, and, maybe more surprisingly, the basic math, the topology of how neural networks are even built.
Right. And our mission here on Tomorrow Unveiled is to cut through all that noise and synthesize these foundational shifts for you. We've structured our analysis around three core pillars that really define this new era.
Okay, let's lay them out.
First up is architectural efficiency. This is all about how models are getting smarter and more stable without just getting, monstrously bigger.
Getting clever instead of just bigger. I like it.
Second, revolutionary hardware. We're talking about technologies that are literally breaking the physical rules of traditional silicon chips.
The GPUs we all know.
Exactly. And third, and this is the one everyone is seeing, the huge shift to embodied and agentic AI. Basically, the move from an AI that chats to an AI that acts and does things in the real world.
So if you really want to understand how AI stops being this digital curiosity and starts becoming a physical, economic, and even geopolitical force, this deep dive is where you need to be.
Let's jump right in with that first pillar, the new architecture paradigm. Because the one thing all our sources agree on is that the future of AI is now about clever engineering, not just brute force. And the absolute star here has to be the work from DeepSeek.
Oh, it's a masterpiece. It really is. What the DeepSeek researchers did was tackle this hidden, crippling problem in training large language models, especially as they get deeper. It's an issue called training instability.
Or exploding gradients.
Exactly, exploding gradients.
Okay, so let's unpack that for a second, because it sounds technical, but it has these massive real-world cost implications. When you're training an LLM, the signal, the information flowing through all these layers can just start amplifying itself, right? Like a feedback loop.
A catastrophic feedback loop. And the numbers that the research team found are they're staggering. They saw that these unconstrained connections in the models, which are, necessary to train them in the first place, could cause the signal to blow up by 3,000 times.
3,000 times.
3,000. Imagine you've got a small signal and it hits an amplifier, but instead of a clean boost, it comes out so loud it just fries the entire system. That's what was happening. The model just becomes mathematically useless.
And the practical result of that is your model just collapses mid-training. All that money, all that energy, all those GPU hours.
Wasted. Just gone. It has been a massive hidden tax on scaling up AI.
So this elegant solution they found, this, manifold constrained hyperconnections? MHC.
MHC, yeah. And the genius of it is that they used a piece of mathematical theory that's almost 60 years old to solve this totally cutting-edge problem. Instead of letting that signal mix chaotically, they put a really strict geometric constraint on it.
A geometric constraint. That sounds very abstract. What did that actually mean inside the model?
So, think of it this way. The parts of the model that mix information from different layers, the matrices, are forced onto something called the Birkhoff polytope.
Okay.
It's a specific mathematical shape. And the important thing about this shape is that it represents all the ways you can combine things perfectly without any chaos or bias.
Yeah.
If you can force your math to happen on that surface, you guarantee stability. It's like, instead of just randomly dumping paints together and getting mud.
You're using a special mixing bowl that guarantees the color always comes out stable and predictable.
That's a perfect analogy. That's exactly it.
So how did they actually enforce that?
Yeah.
Because usually mathematical perfection costs a fortune in computing power.
And this is where it gets so cool. They used something called the Sinkhorn-Knopp algorithm. It was first described back in 1967.
Wow.
Yeah. It's a method for scaling matrices, and by applying it, they turned that chaotic mixing into what's basically a safe weighted average. The math from half a century ago solves the instability of today.
Taking a 1967 algorithm and plugging it into a 2026 neural network. That is amazing. So what were the results? What did the numbers show?
The numbers are just definitive. They took that max signal gain, that explosion potential of 3,000, and they brought it all the way down to 1.6.
So basically zero risk of collapse.
It's effectively gone.
Hmm.
And they use this to train a huge 27 billion parameter model with almost no overhead. Inference was only about 6.7% slower, which is nothing for the stability you gain.
And the bigger picture here is huge, right? Especially when you think about things like chip export restrictions. If you can engineer your way to a powerful model without needing the absolute latest, most power-hungry chip.
You've just changed the game. It shifts the competition away from who has the most hardware to who has the smartest architects. DeepSeek proved that smart design can absolutely trump brute scale.
Speaking of smart design, that brings us to Google's Gemini 3 Flash. Our sources highlighted this one because it breaks another one of those frustrating trade-offs businesses always had to make.
You mean speed versus reasoning?
Exactly. You could have a fast, cheap model that wasn't very bright, or a pro model that was a genius, but was slow and incredibly expensive to run.
Yeah, you had to run two separate systems, basically. One for simple chats, one for the heavy lifting. The launch of Gemini 3 Flash, which our research team corroborated, just makes that whole choice obsolete.
And the key innovation here is something they're calling adaptive thinking. How does that actually work?
It's really clever. The model basically manages its own brain power. It assesses the complexity of the task you give it. If it's a simple question, it uses a low compute fast mode and gives you an answer almost instantly.
Okay.
But if you give it something complex, like a legal contract or a tricky coding problem, it engages a special, dedicated thinking layer for much deeper analysis. It only spins up the heavy machinery when it actually needs it.
So it's smart enough to know when to think hard.
Oh.
That has to translate into some serious performance gains in the real world.
It did, absolutely. The benchmarks were incredible. It achieved what they're calling PhD-level reasoning, scoring over 90% on the GPQA Diamond benchmark. That's a test of graduate-level scientific knowledge.
90%, while being fast.
While being 3 times faster than the previous Pro model, and it cut the cost per token by 30%.
So for a business, this is a no-brainer. You don't need two separate infrastructures anymore. You just have one model that can be both your fast chatbot and your deep reasoning engine.
It collapses the use cases, it collapses the costs, and it gives you reliability. It's a huge win for any enterprise actually trying to deploy this stuff and get a real return on investment.
And there's a third architectural breakthrough our team flagged, this one from Meta. It's called VLGPAY, and it feels like it's the critical link to our next section on, AI in the physical world.
It absolutely is. VLGPAY, that's Vision Language Joint Embedding Predictive Architecture, is all about teaching an AI how the physical world works without being so incredibly inefficient.
What do you mean by inefficient?
Well, think about how traditional models work. They have to generate everything token by token, letter by letter almost. Even if they understand a concept perfectly, they still have to slowly spell it out. It's a huge computational bottleneck.
So if I ask a model to describe how a car engine works, it has to write out a whole essay, word by word.
Exactly. VLGPAY kind of skips that step. Instead of predicting the next word, it predicts the underlying meaning, the semantic concept, in this abstract space they call latent space. It only generates the slow text output when it absolutely has to communicate with a person. The real learning happens at a much deeper conceptual level.
And why is that so important for robotics and understanding the physical world?
Because for a robot to be useful, it needs what's called a world model. It needs to predict what will happen next. If it pushes a cup, it needs to know the cup will slide. Doesn't need to write the words the cup will slide.
It just needs to know the physics intuitively.
Precisely. And because VLGPAY focuses on that abstract prediction, the research team found it's actually better at these world modeling tasks than even much larger general-purpose models. It learns the cause and effect of the real world very, very efficiently.
And the efficiency numbers were just wide. I think the sources said it's 43 times more sample efficient during training.
43 times. It's an enormous number. It means you need way less data, less time, and less energy to teach the model how things work. It's just more elegant. And it really confirms this whole theme. The era of just scaling up is over. Efficiency is the new frontier.
Which brings us perfectly to our second pillar, the hardware wars. Because even with all this architectural efficiency, you still need the hardware to run it on. And the biggest story here, corroborated everywhere, is that the age of the general-purpose GPU is Well, it's ending.
That's a huge statement, but all the data points in that direction. The research team says traditional silicon chips, even the brand new ones like the H100, are hitting what they call the heat wall.
Let's define that. Is the heat wall just a small problem, or is this a fundamental law of physics getting in the way?
It's fundamental physics. For decades, AI progress has been tied to moving tiny electrons around on a chip. When you pack billions of them together and move them fast, you get resistance, and resistance creates heat. So much heat, in fact, that you can't cool the chips fast enough.
So you have to slow them down, which creates latency.
Exactly. You hit a physical and economic ceiling, you just can't scale anymore.
And that wall is what led to maybe the most radical breakthrough our team saw this week, the reveal of LightGen, an all-optical computing chip.
LightGen is just a stunning piece of engineering. It bypasses the problem by changing the particle. Instead of using electrons, it uses photons, particles of light, to do the math.
How does that even work?
It uses the natural physics of light, things like diffraction and interference, to perform the matrix multiplications that are at the heart of all neural networks.
So wait, if there are no electrons, there's no electrical resistance.
It means no heat.
And computation happens at the speed of light, so almost zero latency.
You've just eliminated the entire bottleneck in one go. I mean, assuming they can manufacture it at scale.
The performance claims in the reports were just astronomical. They said it was 100 times faster than an NVIDIA A100 GPU for some tasks.
100 times. For specific jobs, yeah, like generating high-resolution images and video. And the energy efficiency is even more revolutionary. We're talking something like 6.64 by 10 Balers TOPS per watt. That number is just, it's absurdly good. It would completely change the economics of data centers.
Okay, but I have to ask, is this a real replacement for a GPU?
Yeah.
Or is it super specialized?
That's the key question. Right now, it seems very specialized for those generative tasks. It's not a general-purpose chip like a GPU is, but the geopolitical angle here is what our research team really keyed in on.
Right, because if you can't get access to the latest 3-nanometer silicon chips because of export controls,
you just pivot. You pivot to optical computing, which uses a totally different manufacturing process, different materials, everything. It gives you a way to leapfrog the restrictions.
so we could be looking at a future where the global AI stack just splits in two, a Silicon West and a Photonic East.
It's a real possibility. A tech arms race fought on two totally different physics tracks.
And even while that's happening, the silicon industry isn't standing still. It's specializing like crazy to fight off these problems. We saw 2 huge signs of that this week.
The first was a massive strategic move from NVIDIA, a $20 billion non-exclusive licensing deal with a chip startup called Grok.
This is huge. NVIDIA, the king of the general-purpose GPU, is paying $20 billion for a license to specialized hardware. That's them admitting their own architecture isn't the best tool for every job anymore.
It's a massive admission. Grok's tech, their language processing units or LPUs, they offer 10 times faster LLM inference using only 1/10 of the energy.
10 times faster at 1/10 of the power.
Yeah. It confirms the whole industry is moving towards specialized chips just for running models in production, quickly and cheaply. The future is specialization.
And the second big sign was a breakthrough in the physical design of the chips themselves, these monolithic 3D chips.
Right, so this is all about tackling the memory wall. That's the bottleneck you get when your processor is constantly waiting for data to arrive from the memory chips.
I think you used the analogy of an architect who has to keep jogging across the street to the library to get blueprints.
That's the one. It wastes a ton of time and energy. These new 3D chips solve that by basically building the library right inside the architect's office. They stack the memory and the computing elements vertically on top of each other.
So instead of data traveling across a flat chip, it just moves up and down an elevator almost instantly.
Exactly. And that vertical design leads to between 100 and 1,000 times the efficiency in what's called the energy delay product.
So what does that mean in simple terms? 100 to 1,000 times more efficient.
It means you're doing way more useful work with far less wasted energy and almost no waiting time. It's a foundational improvement that makes everything else we've talked about possible.
And you can't have this conversation without talking about the memory itself. Samsung's HBM4 memory got a lot of praise this week.
Oh, HBM high bandwidth memory, is the absolute lifeblood for training these huge models. It's the fuel for the GPUs. And
Yeah.
Samsung's HBM4 is a game changer because it promises to double the number of I/O terminals.
So it's like doubling the number of lanes on the main data highway into the chip.
It is. And it does that while also having a 69% improvement in power efficiency. That is staggering. It helps solve the memory shortages that have been a huge constraint on training bigger and better models. It all points to the same conclusion. The future is specialized and the future is efficient.
And all that efficiency, all that specialized hardware, it's now powering our third pillar. AI gets a body and a job. This week really felt like the moment the transition happened from AI that just chats to AI that acts.
It's moving out of the lab and into production, absolutely. We're seeing autonomous agents become commercially viable almost overnight.
I mean, let's just look at the clearest sign of that.
Yeah.
The acquisition Meta made.
Right, Meta bought a company called Manus for over $2 billion. Manus is an agentic AI startup, and get this, they hit about $100 million in annual recurring revenue in less than a year.
$100 million in ARR in under a year, and then a $2 billion exit.
That is undeniable financial proof. It validates the entire market. It shows that big companies are willing to pay a massive premium for AI systems that can reliably execute complex business workflows. We're talking market research, coding, contract screening.
The product market fit is there. It's not a question anymore.
Not at all. And while Meta was buying a player, OpenAI was getting ready to release its own. The sources all confirmed the imminent launch of the operator.
Which they're calling a computer using agent, or CUA.
And that's exactly what it is. It's an agent designed to use a computer just like a person does. It uses vision AI to see the screen, and it can click buttons, type in forms, scroll. It can operate any user interface.
So instead of me having to do some painful 17-step online process, I can just tell the operator the goal. Like, book me a flight to Boston for next Tuesday, and it will just do it. It'll open the browser and click all the buttons for me.
That's the promise. It completely changes the relationship. We stop thinking about what an AI knows and start thinking about what it can do across every website and application we use. The potential impact on white-collar work is just immense.
And it's not just potential. We're already seeing this tech produce insane results in really specialized fields, like designing semiconductors. Tell us about Agentic CAD.
Agentic CAD is this multi-agent system for complex engineering. You have a manager agent that breaks down the big problem, and then a team of specialized worker agents that run simulations, analyze data, and refine the design.
The time savings here were just, they're hard to believe.
They really are. They gave it the task of designing a state-of-the-art 2-nanometer nanosheet transistor. This is one of the hardest engineering problems in the world.
And how long did it take?
The AI system, Agentic CAD, designed it in 4.2 hours.
4 hours? And the human team?
The human experts needed 7.1 days.
So you're compressing a full week of intense, specialized work by a team of experts into a single afternoon.
That's not just an improvement, that's a phase shift. It's a more than 40-fold acceleration in the pace of innovation.
And this move towards autonomous action is most visible in the consumer space. The physical AI explosion at CES 2026 was all about this.
This is where the smart AI brain we've been talking about finally gets a capable body.
We saw everything from really disruptive pricing to incredibly high-end dexterity. Let's start with the price. Zeroth Robotics M1.
The price point is the whole story there. They unveiled a 15-inch consumer humanoid robot for $2,899.
$2,900. That's incredible.
It is. The research team called this the PC moment for robotics. Before this, a capable humanoid would cost tens, even hundreds of thousands of dollars. They were lab equipment. This price point democratizes the hardware. It opens the floodgates for developers to start building apps for a physical robot in the home.
Then on the other end of the spectrum, you have LG's Colloid robot.
Yeah, the Colloid is the high-end zero-labor home assistant, and its whole focus is on dexterity, on manipulation. It has these 2 7-degree-of-freedom arms and 5-fingered hands.
So it can do things that simpler robots with just basic grippers can't.
Exactly. Complex chores like folding laundry, carefully loading a dishwasher, the really tricky stuff. It's a huge step up in physical competence. Plus, they're powering it with what they call affectionate intelligence, so it can, read your emotions and adapt.
A friendly robot. And then we have Samsung's Bally, the little spherical robot, which finally seems to have found its purpose.
Right. Bally is now integrating Google's Gemini model, so it has that contextual reasoning we talked about. You can give it a high-level goal, like get the living room ready for movie night, and it'll figure out what that means.
But the truly new feature, the one our team really flagged, was the built-in mobile projector.
I thought that was so cool. It can just roll into any room and project a movie or a video call or whatever right onto the wall or the floor. It basically turns the robot into a mobile, ubiquitous screen that follows you around.
So you put it all together, the affordable Xeroth M1, the dexterous LG C-Celoid, the smart Samsung Bally, and it's clear the robot body is finally catching up to the AI brain.
It really is. And with these powerful autonomous agents entering our homes and our workplaces, it just raises so many questions about where society goes from here.
And on that note, we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this huge shift from AI chatting to AI acting, especially with these new robots heading for our homes.
It's a future that's arriving a lot faster than I think anyone expected.
That brings us to our fourth pillar, AI as national strategic infrastructure. The research team noted a definitive shift. Global powers no longer see AI as just a commercial tool. They see it as critical infrastructure, and that's sparking a new kind of geopolitical arms race.
And it's an arms race that might be fundamentally unsustainable, which brings us to the just jaw-dropping scale of xAI's Colossus project.
Right, Elon Musk's project. The plan is to build a supercomputer with over 1 million GPUs.
A million GPUs. It's hard to even wrap your head around that. The power requirement for that cluster is projected to be nearly 2 gigawatts.
2 gigawatts. For context, that's enough power for about 1.5 million homes.
It's the energy footprint of a small city, just to train one company's AI models.
And the way they're planning to get that power has raised some serious red flags for environmental and sustainability groups.
It has. They're literally building a dedicated natural gas power plant with all the pipelines and infrastructure just to feed this one computer. It forces this really difficult conversation about whether the quest for AGI is compatible with global climate goals. Physics and planetary resources are now the main constraint.
And this insane demand for compute is what's driving this push for sovereign AI, with nations trying to build their own AI ecosystems so they're not dependent on anyone else.
And the clearest example of that strategy came from South Korea's SK Telecom. They launched K1, a 519 billion parameter model. But they're not framing it as a product. They're calling it sovereign AI, digital infrastructure for the nation.
What makes it sovereign? What's the strategy?
Its main job is to be a teacher model. It's designed to transfer its knowledge, including all the cultural and linguistic nuances, to smaller, specialized Korean models.
So you use the giant national model to bootstrap a whole ecosystem of smaller, local AIs?
Exactly. It reduces their dependence on foreign tech and keeps control over a critical technology layer. It's an incredibly smart strategy. And we're seeing a parallel move in science with a shift to autonomous scientific research.
This is where the AI isn't just assisting scientists, it's running the experiments itself.
Right. China activated a national AI science network where agents can run entire complex workflows in things like material science.
How much faster is it?
A workflow that would take a human team a full day can now be done in about 1 hour.
An hour versus a day.
It just puts scientific discovery into hyperdrive. And in response, the U.S. is proposing the Genesis mission, which is a similar platform for AI agents to autonomously test hypotheses and design experiments. The whole geopolitical game is shifting from who has the most chips to who controls the pace of scientific discovery itself.
But this incredible acceleration comes with a price, which brings us to our final and maybe most important section. The challenges and critical considerations that our sources say need immediate attention.
And the first one is a huge one: security and governance gaps. As these autonomous agents take over more and more complex workflows, the risks are just exploding.
The research flagged a 43% rise in unexpected AI-driven security incidents in 2025 alone. Why is the risk so much higher with these agents?
It's because their actions are complex and often hard to predict. They're designed to chain together multiple tools to achieve a goal. If something unexpected happens, they might try to self-correct in ways that have disastrous consequences.
It's the black box problem, but for actions, not just decisions.
Exactly. And security groups like OWASP have identified some really specific new risks. The big one is tool misuse and privilege escalation.
Okay, what does that mean?
It's where an agent, doing a seemingly simple task, chains together a few harmless tools in an unexpected way to gain access to things it shouldn't.
So an agent that's just supposed to be doing market research could accidentally figure out how to chain 3 different database tools together and end up with access to the entire company's financial records.
That's the nightmare scenario, yes. The agent isn't malicious, it's just trying to complete its goal, and it stumbles into a catastrophic security hole. Another big one is memory poisoning.
Corrupting the agent's memory.
Yeah. An attacker subtly feeds it bad information over time, corrupting its long-term memory. It's like a slow-acting virus that changes the agent's behavior. It might start making consistently biased decisions or ignoring critical alerts. It's incredibly hard to detect because it's not a single bug, it's a systemic drift.
And this is all happening while the rules are a complete mess. The sources all pointed to regulatory fragmentation.
It's chaos. In the US, you have the federal government trying to create one set of rules, but then states like California are creating their own stricter rules.
So a company trying to deploy an autonomous agent across the country has to navigate 50 different sets of compliance laws.
It's a logistical nightmare, and it creates uncertainty right when we need clarity for safe deployment. And that ties right into the second major challenge, ethical opacity and the AI slop crisis.
Let's start with the ethical side. The problem of automated inequality seems to be getting worse, not better.
It is. As these models get better and score 90% on PhD-level exams, they also become more of a black box. Their reasoning is so complex that they literally can't explain why they made a high-stakes decision. This is black box 2.0.
So any bias in the system is completely invisible and unauditable. You can't fix what you can't see. And regulations like the EU AI Act that require explainable AI are running up against a wall of pure mathematics.
They are. And that opacity is being compounded by the AI slop crisis. Just the sheer volume of low-quality AI-generated content flooding the internet.
To the point where search engines and social platforms are now introducing verified human toggles.
It's a defense mechanism. People want to filter out the noise, but it creates this bizarre paradox.
Which is?
The human web, which is the source of all the high-quality data we need to train the next generation of AI, is retreating behind these verification walls.
So today's AI is poisoning the well for tomorrow's AI.
It's a self-defeating cycle, and we need to figure it out quickly. And that brings us to the final challenge, which is about those robots we were so excited about: reliability and physical reality.
The promise is huge, but the reality of a messy human home is the ultimate test.
And that's where we see the demo versus reality gap. The demos are always in these pristine, perfect environments. But in the real world, the sources say these wheeled robots still get completely stumped by stairs, by clutter, by a stray power cord on the floor.
Right. And if you've just spent nearly $3,000 on a robot like the Zeroth M1 and it gets stuck on your rug half the time, that's a problem.
It's a huge barrier to adoption. The hardware is getting there, the intelligence is there, but reliably navigating the chaos of a normal house is still the final boss of robotics. The market is demanding utility, not just a cool demo.
And that demand for utility really brings us to the summary of this whole week. The central conclusion from all the data our team compiled for Tomorrow Unveiled is that this was the week the transition became official.
We've moved past the old idea that you just have to build bigger models. Architectural innovation, things like DeepSeek's MHC and Gemini's adaptive thinking, is now delivering top-tier intelligence, but efficiently.
And that efficient AI brain now has a competent body. It has the agentic software to actually start doing work, whether that's designing a chip or rolling through your living room.
The consensus from the industry is crystal clear. 2026 is the show me the money year. Businesses and consumers are demanding a real return on investment. They want reliable, useful AI systems. The time for just experiments is over.
So with all that, what does this acceleration mean for you listening to this right now? Here's our final provocative thought, and it comes from data corroborated by the UK AI Safety Institute. The time it takes for AI capabilities to double without any human help is now approximately every 8 months.
Every 8 months, that is just a blistering pace. It means the AI of today is already twice as capable as it was last spring.
So if that trend continues, you have to ask yourself, by the end of this year, 2026, what highly specialized PhD-level function will an affordable, autonomous agent be able to reliably perform for you?
Will it be doing your complex taxes? Managing your investment portfolio, designing a custom health plan based on your real-time data?
The pace of change has never been this fast. And the skills that will be valuable tomorrow are being defined by the agents that are shipping today.
That is the question that's going to define the rest of this year.
If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
Thank you for joining this deep dive into the world of artificial intelligence. We look forward to unveiling more tomorrow.